Okay, so we want to finish up our review for your second semester exam. And so our next category was energy and thermodynamics. In energy and thermodynamics, we talked about what is an endothermic and an exothermic reaction. Remember, one that takes in the energy, so something that needs energy to work. And exothermic is a reaction that gives off energy. So these would feel cold to us, these would feel hot to us, okay? And so you need to remember that because we will have questions. So like, for example, we ask you, what is melting ice? Well, melting ice needs to pull energy into itself. So melting ice is actually endothermic, okay? So remember those kind of ideas. And then we also remember we talked about what is energy. We have different kinds of energy scales. So temperature, and temperature is the measure of the kinetic energy. It's how much the object is moving. So when it's moving, and we know that it has energy, so if I can put a thermometer into this table and I can get a measurement of a temperature from this table, that means this table somehow is moving or has a vibration because it has kinetic energy. So that's what we talked about. And there's different energy scales. There's the Celsius temperature scale, and there's the Kelvin energy scale. And the Kelvin energy scale is higher in number. So if you want to convert and you want to go this way, the number is 273. We add it to go up to Kelvin, and of course subtract to go back. So you should know how to use the two energy scales, okay, that we have, our temperature scales. Then as we went on, we talked about taking materials and heating materials up. So we can take some ice, let's say we have ice down at -10, and we warm it up to 0 degrees, and then that ice begins to melt, okay? And if we want to get the ice all melted, we add more energy. That ice then can heat up to 100 degrees, then we would run across boiling, and then that material would boil, and then after that we could then raise it up higher again. So we had our two situations, our temperature scales. We had solid changing into liquid or vice versa, and liquid changing into gas, and we wanted to know how can we measure the energy in all of these changes. And so our first energy equation was called calorimetry. Calorimetry is the study of energy, which is joules, when a system, which means a material, when the mass undergoes a change in temperature. But it depends on what you're heating up. Not all materials change their temperature quickly or easily. So we gave you the example about sand and water. You go to the beach and the sand is extremely hot in the summertime, it's burning your feet, but you jump into Lake Michigan, it's been in the sun the same amount of time that day, but the lake is really cold. That's because water and sand, which is silicon dioxide, respond to heat differently. And so to find the temperature change and the situation, if the temperature is going to change, you need to know the CP, or specific heat. And so we have all kinds of specific heats. Water CP value is 4.08 joules per gram degrees Celsius. I believe the specific heat, this is for water, specific heat for aluminum is 0.798 joules per gram degrees Celsius. You do not need to have any of these numbers memorized. They will be on the test if you need to use them. They're called specific heats. If you don't remember them, please look them up and think them through, okay? But we are going to give you calorimetry problems. We're going to give you problems where a material is raising its temperature, and we're giving it specific heat. How much joules of energy will it need? Okay, so you'll need to know that, and so be careful. But if you get to a point where, remember, if we're at a phase change, the energy going in is not raising the temperature. So we took boiling water, put a thermometer in it, and the water never changed temperature. It stayed right at 100 degrees. It bounced around a little bit, but it doesn't change. So the energy now, instead of going into changing the temperature, it's going into stretching or changing the molecular structure. And when that happens, the way we find energy that's being used in those situations, because the ice is still absorbing energy to change into water, and the water is still absorbing energy to change into a gas, we need a different energy equation, and it's called the enthalpy equation, and you need to know the mass and the enthalpy, and enthalpy is delta H. It's the energy to change a system from one type to another. And so if I want to find the energy of this system, there is the energy of enthalpy for water again, going from a liquid to a solid, or a solid to a liquid, and that is 334 joules per gram. You do not need to memorize those numbers. We'll give you those in the test. You just need to know when to use the formulas correctly. You use this formula with the enthalpy when you're going through phase changes. You need to use the calorimetry equation when the material is raising its temperature. So if they ever give you a temperature change, 10 to 15 degrees, -5 to -40 degrees, then you'll be using the calorimetry equation. So you need to know how to use those equations at the proper time in the test, okay? So that takes care of the energy side of our problems, thermodynamics. We went through all those. And so our last category just really goes into what we talked about as the gas laws. And the gas laws, remember, as just being the ideal, we used a combined gas law. And in the combined gas law, we had all of our other gas laws, the Boyle's law, the Charles law. It was P1, V1, T1 equals P2, V2, and T2. And so each time you use this law, it means there's no change. Remember, you use this one if there's no grams or moles being mentioned. And so you do this mathematics and you just rearrange for whatever you need. You have your two scenarios, your two cases, and it's really quite simple. Then we have the ideal gas law. And the ideal gas law is when we take PV equals nRT, and in this case you need to know the ideal gas constant, which is 0.0821 with its units too. Make sure you remember to write down its units, which is mole times Kelvin times liters times atmospheres. And remember, there's a restriction on both of these laws. Temperature must always be in kelvins. Okay? So remember that, and over here the pressure must be in atmospheres, but pressure can be in any of the units, kilopascals, any kind of units you need. So we have the combined gas laws we did, and the ideal gas law. These are laws that are mathematical laws that will also be on the test. Remember, we taught you a quick little rule that when you're studying these laws, you can actually look at this idea that if we're studying this law and temperature's not being used, you just remove it from the equation. And if you want to know how they're related, the temperature is constant, you put the finger there, and as you raise the volume, the pressure goes down, so it's called an inverse relationship. One goes up, the other goes down. Let's say we're going to study pressure and temperature, so you throw a can in the fire, and so the volume's not changing because the can is solid. So we put our finger here. Well, as the temperature goes up in the fire, the pressure goes up also, so they're directly related, and they end up causing the can possibly to explode. So that's called a direct relationship when they change in both directions. So make sure you know your relationships, make sure you know your mathematical equations, and how to do that, okay? So that was the gas laws by Charles, Gay-Lussac, and Boyle's law, okay? Make sure you can use them efficiently and quickly on the test. There are some problems, not a ton, but there are enough for you guys to have to do some work on the test. And then of course the last unit we got and we did was only this very, very, very short unit on solutions. And in solutions, we talked about what is a solute, what is a solvent, and a solute is what gets dissolved, so like sugar and water. The sugar is what's being dissolved, so that's the solute. The solvent will be the water. But the air is also a solution around us that we're breathing in, and air, when it's being breathed in, isn't two different materials. So it is oxygen and nitrogen, that kind of stuff. But the problem is which one is the solvent, which one's the solute. The greater in amount is nitrogen in the air that we breathe, so it makes it the solvent. So this is the greater in the amount, and the solute is the oxygen that's mixed in there, or the water in the air, the moisture. Okay? Well, you should also know what an electrolyte is. An electrolyte is a solute that breaks down into ions and then can conduct electricity. So salt is an example of that. Salt, when it breaks down into its two ions that make it up. Okay? And then electricity can actually jump through and is a conductor. So electrolytes are things that we drink or eat in our body that help us conduct electricity from our brains to our arms and our legs and that kind of stuff. And if a material breaks down and dissolves like sugar and doesn't let electricity go through, it is called a non-electrolyte. Okay, and a non-electrolyte is a material that actually does not break down into ions. So make sure you know the basics about solutions and what's electrolyte, ions, non-electrolytes, and that kind of stuff. And so what makes up a solution and what parts of it. So just some basic definitions and ideas, okay? So make sure you have these ideas written down. Make sure you have some example problems. Make sure you have some numbers worked out. If you don't know how to rearrange the equation, I highly suggest that you take your equations and maybe if you're bad at pushing the Rn, it's now going to be, if I want to push them on the other side, it is going to be P times V over R and T. You're free to rearrange everything, okay? So if you want to have T by itself, then T equals, of course, P over V and then times N and R. So you can do that if you want. So if you have to do any kind of pre-math so you don't get it wrong rearranging on the final exam, please do that for yourself. That's okay. So you can show all the rearrangements that you want to make sure. So if you can't solve for T on the bottom very well, you always get that wrong, preset it up. Have it all set up so you can just plug the numbers in. You've got the correct formula right there on your help sheet, okay? But we're not going to supply that. And you have to supply all your own equations, but we will supply numbers like CP, things that you need to know about. We're going to supply that kind of things. We will give you a periodic table so you don't have to memorize any of your formula weights. You can find them and do them, but make sure you have good enough examples and stuff that you need, okay?